This cartoon made me chuckle, and it's especially appropriate for section 6-7. We're going to be looking at the degrees of polynomials and relating that with the number of roots. Looking at a polynomial and finding each of its factors and knowing exactly how many and what kind of factors to find. So let's get started. It's kind of a fun section. So I'm looking at the graph of this polynomial function. I can see that it appears to be even because from what I see, both of the end behaviors are heading towards positive infinity. And indeed, it says find the factored form of this degree 6 polynomial function. Remember what degree means, degree 6. The degree 6 means that the highest exponent in the polynomial is 6. So how do we know how that affects the factors? Well, if you have factors, it's things that you are multiplying together to get that polynomial, and there must be 6 of them, because if each one has an x in it, when I multiply these all together, I'm going to get 1, 2, 3, 4, 5, 6 x's being multiplied together, which is going to be x to the 6th. There might be a coefficient in front of it, but the main thing we're looking at is the degree of the function would be 6. So I must have 6 different factored groups because it is a degree 6 polynomial function. Now I'm looking at the graph here and I see a 0 at 2. I see a 0 at 3. I see a double 0 at -1. That means, remember, that it's been used twice. And I see a double 0 at -3. Now, let's go ahead and fill in the factor groups that we have so far. And remember that if x, or the 0, is -3, then you have to move it over the equal sign to make it into a factor group. So the first one we'll do is x plus 3. Again, it's used twice, so I'm going to put it in twice. Plus 1 is used twice. Minus 2 is used once. And minus 3 is used once. And look at that. I have filled up each of my factor parentheses. So by just looking at this particular graph, I can factor it. Isn't that a breath of fresh air? So let's turn in your book to page 383 and get started. The first concept summary is about zeros, factors, roots, and intercepts. It says, let p of x equal a sub n, x to the n, plus ... plus a sub 1, x to the 1, plus a sub 0 be a polynomial function. Remember that this is simply the algebraic notation for a polynomial function. It says if it's a polynomial, then the following statements are true. And then it says c is a 0 of p of x. And where did c come from? There is no c in this polynomial algebraic thing. And are they talking about ax squared plus bx plus c? No, they are not. What they are talking about is they are saying that any factor can be written in the form of x minus c. So this right here would be the 0 of the function. That's what they're letting c stand for. C is the 0. When you put it into the factor, you have to move it across the equal sign, and so it becomes x minus c. So it says c is a 0, then c is also a root or a solution, that if you put p of c in, you should get 0. I don't know why they put an x there. X minus c is a factor. C is a real number, then c, the point c0 is an x-intercept of the graph. Now down here they do an example trying to show you what they're talking about. So here is the polynomial function, and this is its graph. The zeros are at -3, -2, 1, and 2. That means that they are also roots and also solutions. And if we were to take p of -3, it would equal 0. P of negative 2 would equal 0, p of 1 would equal 0, and p of 2 would equal 0. If we turned those into factor groups, it becomes x plus c multiplied by x plus 2 multiplied by x minus 1 multiplied by x minus 2. And then the x-intercepts are negative 3, 0, negative 2, 0, 1, 0, and 2, 0. I think that you knew all of this, but here it all is in one box. Go ahead and read the next part, and we will look at the fundamental theorem of algebra. All right, this has to be the most obvious statement of math kind. It says every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. Now, if you remember when we talked about complex numbers, we said complex numbers are in the form of a plus bi, and that is all numbers. Now, these fit into two groups, real, and if you have real numbers, then b equals 0. And if you have imaginary numbers, then b does not equal 0. So what is this fundamental theorem of algebra saying? It says if you have degree greater than 0, so here's a degree greater than 0, y equals x to the 1, it has at least one root, or you could substitute that word with solution, in the set of complex numbers. In other words, it either has a real or an imaginary root. The only thing I have to say about the fundamental theorem of algebra is duh. Let's move along. I'm going to go out of order, and I'm going to jump down to the corollary to the fundamental theorem of algebra on the bottom of page 384. Not all books separate the fundamental theorem of algebra with this corollary. A lot of them say it all together in one group, and this really is the more important thought here. And that is, if you have a polynomial equation of degree n, whatever that is, it has exactly n roots in the set of complex numbers, including repeated roots. So if you have something to the third power, there are going to be 3 roots. Some of them might be real, some of them might be imaginary, some of them might be repeated, but there will definitely be 3 parenthesis sets being multiplied together to get this polynomial. If it's to the 4th degree, there are 4 roots. If it's to the 5th degree, there are 5 roots. And that is a very important thing to know. So let's go back up to example 1 then. Okay, let's look at example 1. Determine the number and the type of roots. Now, when you first look at this example, it looks like that they are looking at the graph and then from that factoring, but really, indeed, they are not. They are doing their check with the graph. So what are they doing in this example? First of all, they are factoring, and then they are using the factors to determine the zeros, and then they are checking their work with their graph. So let's proceed in that manner. We have x squared plus 6x plus 9, which hopefully by now, if you think half of 6 is 3, and if I square it I get 9, this is indeed a perfect square. Or you might think, what are the factors of 9 that add up to 6? Either way, you end up with x plus 3, the quantity squared. Once you have that, you square root both sides, and you end up with, I have a 0 at x equals negative 3. You also know it's being used twice since you had x plus 3, the quantity squared, which means indeed there is a parabola sitting right on x equals negative 3. All right, let's look at example B. Example B, you have x to the third plus 25x. You take out the greatest common factor, which is x. Then, since this is x squared plus 25, remember that that is a parabola that has been moved up 25, which means imaginary roots. So when we go to solve, we put each part equal to 0. X equals 0 and x squared plus 25 equals 0. X squared equals negative 25, x equals plus or minus 5i. So we have 2 imaginary roots and we have 1 real root. if we were to write this in linear factored form, meaning that each factor has degree 1, we would have x, we would have x minus 5i, and we would have x plus 5i. And that would be our linear factored form. All right, get ready to do the check your progress. Remember, you are starting with factoring. Factor first, then check it with your graph. Please take the time to do this. You know what will be on the non-calculator page. All right, look at the next screen, pause it, and give it a try. One more thing, I just did the check your progress problems, and 1C cannot be solved by factoring. 1C can only be solved by graphing, just so you know. These are the check your progress problems for section 1. Notice that 1C can only be solved through graphing. The rest can be factored. Pause the video and then I will explain the answers. If you look at the answers and you know them, you'll be able just to skip my explanation, but if you want explanation, you can listen to it. So pause and work. Here are the answers to 1A and 1B. On 1A, you look for the common factor. It's x, which left you with x squared plus 2. You make that x squared equals negative 2, which gives you plus or minus the square root of 2i. If you were to write this back in factored form, the factored form would be x multiplied by the quantity of x minus 2i multiplied by the quantity of x plus 2i. Notice that the actual zeros are x equals 0 and x equals positive square root of 2i and x equals negative square root of 2i. For 1b, you have the difference of two perfect squares, which gives you x squared plus 4 and x squared minus 4. X squared plus 4 equals 0. That means x squared equals negative 4, which gives you plus or minus 2i. X squared minus 4 equals 0, which gives you x equals plus or minus 2. And then these are your zeros. There are 4 of them. If you were to put it into factored form, you would write the zeros with the 3 factors so that, or excuse me, the 4 factors so that they were multiplied together. You would end up with x to the 4th minus 16. All right, now I'm going to do the next 2. Again, if you don't need the explanation, just skip over it and just look at the answers. The answer to 1C, if you try to factor it, you quickly find out that it does not factor. So if you put that in your y equals and graph it, you see a 0 at x equals negative 5, x equals negative 1, and x equals 2, and there is your factored form. Now let's look at 1D. These are the answers to 1D. A couple of things to notice. We have 2 imaginary roots and also 1 real root. You do need to put this in as 3x minus 1, not x minus 1/3. Why? Because when you're in the factored form, when you multiply these 3 factors back together, you need to get 3x to the 3rd minus x squared plus 9x minus 3. And the only way to get that 3x to the 3rd is to have a 3x in your factor set. But the zeros are x equals 1/3 and x equals plus or minus square root of 3i. Descartes' rule of signs is kind of interesting, actually. First of all, it starts out with let p of x equal the algebraic form of the polynomial with real coefficients. Notice with real coefficients. Then the number of positive real zeros of the function, like 2, 4, even the square root of 3, you know, it doesn't have to be rational, it just says positive and real, is the same as the number of changes in the sign in the coefficients of the terms, or is less than this by an even number. Okay. And also, if you plug in a negative x and then count the number of changes in the signs of the coefficients, then the number of negative real zeros is the same as the number of changes in the signs of the coefficients, or less than this by an even number. Now I think from here we need to go right to the example. I guess those, oh, there we go. All right. So here's our example, and they give us a very nice polynomial, x to the 6th plus 3x to the 5 minus 4x to the 4th minus 6x to the 3rd plus x squared minus 8x plus 5. Now what they're saying is, look at the sign change. This is positive. This is positive. Was there a sign change? No. Was there a sign change here? Yes, it went from positive to negative. How about the next one? Nope. Yes, from negative 6 to positive 1. Yes, from positive 1 to negative 8. Yes, from negative 8 to positive 5. So there were 1, 2, 3, 4 sign changes, which means the number of real positive zeros could be 4, could be 2, and could be 0, because it goes down by even numbers. So that's what this box is here. Now, what about when we put in negative x? When we put in negative x, then we are looking then for sign changes. We plug in negative x to the 6th, it becomes positive. We put in negative x to the 5th, this becomes negative. This 3 would be negative. We plug in a negative x here, it still stays negative. Put in a negative x here, it becomes positive, because you'd have negative 1 times negative 6. Negative x squared stays positive. Negative times negative is a positive, and then a positive. So you've just plugged negative x's in, taken them to the powers, multiplied them by the coefficients to see what you come up with. So sign changes. Yes, no, yes, and that's it. So there's only 2 sign changes, which means there could be 2 negative zeros, or there could be 0 negative real zeros. So we pair that up. If there are 4 positive real zeros and 2 negative real zeros, then there would be 0 imaginary ones. If there were 4 and there were 0 of them, then there would have to be 2 imaginaries. Why? Why would there have to be? Because they have to equal 6, the degree of the function. So what is this table doing? This table is just pairing all of the possibilities between positive real zeros, negative real zeros, and imaginary zeros. What are the possibilities? And so they put them all together for all of the possible combinations of types of zeros based on the sign changes. Kind of interesting. So let's have you do the check your progress. Take a look at the check your progress and put together a table of possible types of zeros based on the sign changes for f of x and for f of negative x. And note how many total zeros you have to have. Okay, good luck. Okay, take a look at it. There were 2 sign changes with h of x. So that means it's possible that there are 2 possible real zeros or 0 real positive zeros. So here's my positive real zeros. I could have 2 with 3 of the negatives. That would leave 0 imaginaries just because it has to be a total of 5. There could be 2 reals and just 1 negative real, which means to total 5 there would have to be 2 imaginaries. There could be 0 positive reals, which would, or 3 negative reals and 2 imaginaries to give us the total of 5, or 0 reals, 1 negative, which would leave us with 4 imaginaries, which would have to total 5. Remember, imaginary zeros have to always travel in pairs of complex conjugates, so you'll always have an even number of imaginary zeros. Okay, example 3, don't read the whole thing because I think they get a little ridiculous. We're going to do this slightly differently. It says use synthetic substitution to find the zeros, and they give us a nice function, which is very nice of them. And here it is, f of x equals x to the fourth minus 18x squared plus 12x plus 80. Now, it's good to look at it and say, how many zeros do I need to find? Well, it's degree 4. It needs to have 4 real zeros. And you can look at the sign changes. Yeah, we're either going to have 2 positive real zeros or no positive real zeros. We're either going to have 2 negative real zeros or no negative real zeros. Okay, that's all well and good. But then for the next part, they have you make a table and start guessing and checking. No, we're not going to do that. We are going to go to the graph. So I'm going to graph it on my calculator and stick it on the screen. Just a second. And here it is. Now you can see that we have a real zero at negative 2. Now I wouldn't always assume that. I would check on my calculator. I would use second calc and I would check the value, put in a negative 2, make sure it is a 0. So I see that I have x equals negative 2, and I see that I have x equals negative 4. I see one turning point. I also see another turning point here, which could represent 2 more zeros that I suspect might be imaginary. So how do I get to those imaginary zeros? Well, I have to use synthetic, they say substitution, I would say division, to find those other zeros. So what am I going to do? I'm going to take my first zero, which is negative 2, and I'm going to set up synthetic division. The coefficient of x to the fourth is 1. Coefficient of x to the third is 0. Coefficient of x squared is negative 18, and then 12, and then 80. And I should get 0 remainder because it is a 0. I drop my 1, I get negative 2, I add, multiply, add, multiply, add, multiply, and sure enough, I have a 0 for remainder. And this is my constant is 40. Negative 14 is the coefficient of x to the 1. Negative 2 is the coefficient of x squared. And 1 is the coefficient of x cubed. And that's when you get, when you divide out x, the factor x plus 2 from the polynomial. So now I'm going to divide out negative 4. Notice I'm starting with the results that I've already divided out. So I'm going to drop the 1, and I get negative 4. I add, I get negative 6. I multiply, I get 24. I add, I get 10. I multiply, I get negative 40. I add, I get 0. It means I'm left with x squared minus 6x plus 10. Does that factor? No. No factors of 10 add up to negative 6, but I can use the quadratic formula now to find my imaginary zeros. So I'm going to say 6 plus or minus the square root of b squared, which is 36, minus 4 times 1 times 10, all over 2a. So this is 6 plus or minus the square root of 36 subtract 40 is negative 4, all over 2. So what are these zeros? They are x equals 3 plus I, and x equals 3 minus I, because 6 divided by 2 would be 3. This is going to be 2I, and when I take 2I and I divide by 2, I just get a simple I. And it's going to be plus or minus, of course. What is my factored form of this polynomial? Well, my factored form, I'm going to make it red and just kind of write it in the middle where I've got a little space left, is x plus 2, x plus 4, x minus 3 minus I, x minus 3 plus I. Okay, for the not the U-tries, but the check your progress, I'm going to give you the one in the book, but I'm also going to give you another one, a 3B, that will have a double zero. Make sure you divide out the double zero twice before you look for the other solutions. The other solutions might be imaginary or they might be irrational. Please give exact answers for your zeros. Good luck. Here is the book's check your progress. F of x equals x to the third plus 2x squared plus 9x plus 18. And then 3b is my check your progress, x to the fourth minus 6x to the third minus 5x squared plus 72x minus 80. I'm very sorry about the poor penmanship, but the stylist I have, I'm really doing the best I can. Thanks. Good luck. Pause the video and try them. Get all the zeros and write in factored form. Thanks. Okay, here are the zeros and the factored forms of each of these equations. Of number 3 in the book, it's x equals negative 2, x equals 3i, and negative 3i, making the factored form x plus the quantity of x plus 2 times the quantity of x minus 3i times the quantity of x plus 3i. The zeros on 3b, you've got a double zero at x equals 4, which means you have to divide it out twice. Then your other zeros are negative 1 plus the square root of 6 and negative 1 minus the square root of 6. Okay, let's move along. I hope you took notes on the complex conjugate theorem. I didn't think it was important to go over because we've already talked about it, but you should read it over and take some notes on it. Now, example 4, we have been doing right along, so this won't be anything too new. It says, write a polynomial function of least degree with integral coefficients, the zeros of which include negative 1 and 5 minus I. Now, so you have an x equals negative 1, which gives you the factor x plus 1, which you see here. Then you have x equals 5 minus I, which, remember, you're moving everything over the equal sign. So it ends up being x minus 5 plus I. And then that's the second. Well, they do it like this. I think that's a lot more confusing personally. And then you have the third one, x equals 5 plus I, and that would give you the factor x minus 5 minus I. Now, they show you a very difficult way, I suppose, and it might seem easy to you, but to me it seems more difficult. I'm going to change the screen and show you how I would multiply these together, just simply because I think it's easier. So let's change the screen. All right, this is how I would multiply this out. I would remember that I'm using the distributive property, and I'm going to take x times each of the things in the next parenthesis set. So that would be x times x is x squared, and then minus 5x, and then minus x times I. So I've just used up this x. Now I'm going to do the negative 5. So it's negative 5x. I have a positive 25. I'm going to put it over here because it doesn't line up. It's not a common term. And then negative 5 times negative I is positive 5i. All right, now I'm going to multiply everything by I. X times I is positive xi. Then positive 5i. And then, excuse me, I'm at negative 5i, and then negative I squared. So I'm going to combine my like terms. I have an x squared. I have a negative 10x. These cancel out. These cancel out. Remember, negative I squared means negative 1, which is really positive 1. So this is plus 26. Once I have this, I'm going to multiply by x plus 1. I'm going to multiply x times each of the three terms. X cubed minus 10x squared plus 26x. Now I'm going to multiply 1 by each of the terms. X squared minus 10x plus 26. Combine my like terms. X cubed minus 9x squared plus 16x plus 26. This is the function that they started with. And if, I'm just checking my answer to make sure I got the same thing that they did, yep. If you look at example 4 and you think that that makes more sense to you, that's fine. You can do it that way. I just tend to do it this way. It's what makes sense to me. So go ahead and do the number 4, check your progress. Here is the check your progress. Give it a try, pause the video, and then come back and check your answer. Good luck. Okay, let's see if that's what you got. We're done with section 6.7, the reading portion. Good luck. I hope you took good notes. It's kind of a nice little section. I like finding the roots of polynomials. I hope you grow to like it too. See you soon. Bye-bye.